Good morning, students. Can you see my writing pad?
Yes, sir.
Thank you. Today, we want to look at how do we change a low-pass filter to a high-pass filter if the filter is FIR. Okay. And the FIR filter we will be using is the moving average filter, because that's the only FIR filter, low-pass filter we know. Okay, so far. Okay. So we're going to be looking at the 5-term moving average filter. So that has a cutoff frequency of pi over 5, or 0.6283 radians. Okay. So we know then that the impulse response is as shown. Okay, because the difference equation was this. Okay. That was the difference equation. Okay. I'm letting the latecomers in. Now that's a low-pass filter. We showed that was a low-pass filter. We showed that using an octave. And now, how do we convert to the equivalent high-pass filter? We use this law here. Okay. Says the impulse response of the high-pass filter equals -1 to the power of n times the impulse response of the low-pass filter. Okay. That's easy. All this means here is this value here, -1 is 0. Okay. Plus, and is of course 1. And then -1 to the power of 1 is of course -1. Okay. So -1 to n is +1 for n even, equals -1 for n odd. Okay. So all that means then, take the original impulse response and every other point, make it negative of what it is. So this is positive, negative, positive, negative, positive. Okay. So all we have to do is take the original low-pass filter, okay, and make every other term negative. Okay. That's what this means. Okay. Let's do that then. Let's do that using octave. Okay. And we go to 5-term right here. Okay. That's not the one I did today. It's this one. No. All right, let's do this one. Back. So let me go back to the page for a second, the writing pad for a second. Okay, please take a snip. I'm going to the next page. All right. So this is the impulse response of the low pass filter. All right. So the transfer function, simply this. Okay. So using our rule then, we convert to a high pass filter by simply changing the sign of every other one. So the H of Z then for the high pass filter. So how many people are with us now? Okay, we're missing one. Who's that? What are we missing?
Look like Anderson.
Yes, Anderson. Yes, thank you. Okay. So this is for low pass filter. It's for the high pass filter. 1 minus -1 plus z to -2 minus z to -3 plus z to -4. All right. I'm going to plot this now. I'm going to plot this to show you that that's a high pass filter. So let's go back to octave. There's octave. Okay. So we plot the digital frequency. I mean, we get digital frequency values, and now here's the frequency response. Okay. For the 5-term moving average filter. Notice positive, negative, positive, negative, positive. And then we do the same thing with the real part and the imaginary part. Okay? Positive, negative, positive, negative, positive. And then, of course, for the imaginary part, there is, from here, you see that's negative. So that's where the negative sign comes from. Negative, positive, negative, positive. And when we plot this, there's There's your high pass filter. Right? So you're passing high frequencies. It's passing frequencies near pi. Of course, pi is a high frequency in digital. So what should the cutoff frequency of this be? What should the cutoff frequency be?
Is it still pi over 5?
How can that be possible, Mr. Buchan? How does that make sense?
That's for a low pass filter, sorry.
Okay, so knowing that for the low pass filter is pi over 5, what should it be for the? Look at the symmetry. What should it be for the high pass filter?
I think this one I went
Nobody? Nobody can use the symmetry? Remind that we have the same curve, but it's flipped over pi over 4. No, pi over 2. Just take this curve and flip it over the pi over 2 axis. So the cutoff frequency for the low pass filter is pi over m. Okay, so the cutoff frequency for the high pass filter will be pi minus pi over m. Now, what is pi minus pi over 5? What is pi minus pi? What is pi? How much?
4 pi over 5.
Which is how much? 4 pi over 5 don't help you much. You know.
2.513.
Yes. Okay. 2.51. Remember now, that theoretical answer is just an approximate answer. You remember that from last class? So, you're looking down here to the left-hand corner. We're going up here, and what value we want to find? What value do we want to find?
That's the 0.70, right? 707 or something like that.
Yeah, exactly. So if you look down there in the left-hand corner, you see I have that magnitude of 0.707, or close enough anyway. And what frequency does it say? It says 2.57. So that's very close to the theoretical answer. Any questions about this? So the moral to the story is we simply change a low pass filter and a high pass filter by changing every other sign. And it goes the other way. If I have a high pass filter, and I do the same transformation, I change every other sign and the impulse response, then I will get the equivalent low pass filter. Any difficulty with that? There's another thing I want to do. We could also plot the magnitude in dB. You could plot the magnitude in dB simply by saying magnitude equals right here 20 times log 10 of the magnitude. Yeah, so we just said take 20 log 10 of that, and we could put dB here, and we save it. And try it again. Oh, okay. Let me show you code, and then you can tell me what I did wrong. Look at the code. What did I do wrong?
I'd assume you need to add one.
I need what?
Colon.
So again?
Add one more. Add one more apostrophe, I mean.
Where?
Where DB is. And if you use one.
No.
Oh.
You talking about line 36?
Sorry, that looked good. I just realized where the next apostrophe was.
What am I doing wrong? What does that line do there? The line I just highlighted, what does that line do?
Not dealing with the range and the X and Y axis.
Yeah,
Exactly. So I'm saying the x-axis, the minimum value is 0, the maximum is pi, which is good. I mean, that's what we have. And from the previous graph, before I put the dB in, I said the minimum is 0 and the maximum is 1. Now the minimum y is negative infinity and the maximum is 0. So I have to get rid of this line. And the easiest way to get rid of this line is just to put a percentage sign in front of it. And save it. And try it again. There it is. That's the dB plot. And we notice here that that's 0 dB, as it should be. And then we find the negative 3 dB. Negative 3 dB is about here. No. Go down further. About there. And there you see, down the left-hand corner, what's the frequency? 2.5. 2.513 radians, which is about what we expect. Because negative 3 dB now is the cutoff. Negative 3 dB is the magnitude at the cutoff frequency. Okay. And out here, we call this the first side lobe. That's what we call it, side lobes. And you think this is only down about negative, well, theoretically, negative 13, theoretically. But here it's more like negative 12. maybe 12 dB, which isn't very good. You're not suppressing the frequencies from here to, well, the frequencies from 0 to here. You're not suppressing those very well. They only negative 10 dB, negative 12 dB below what you want. So you're not getting rid of them very much. You're getting rid of them by a factor of about 10. No, not 10. About 3. Okay. You want this to be down to negative infinity. So this is not a very good filter at all. But I told you that already. So we don't use it so much for its filtering capabilities. We use it for what it does in the time domain. It smooths out those peaks and those valleys in the time domain. That if that's what we want to do, then we use this filter. Okay. There's something else I can do. Instead of plotting versus digital frequency, I convert that digital frequency to analog frequency. How do I do that? How do I convert those digital frequencies to analog frequencies? So mag goes to mag dB. Oh, no, let me put it. Mag dB is 20 log mag. But we know that. So that's how we convert the y-axis. How do you convert the x-axis? Analog frequency equals what? What is analog frequency? How do you get the analog frequency from the digital frequency? This goes back to the first or second class, probably the second class.
You mean like the FM and then the FS minus FM?
I mean, what is the relationship between digital frequency and analog frequency? That's what I mean. Omega C equals? No, sorry. Omega equals? What does omega equal?
It's not FS divided
It's not what? Sorry?
by FS divided by 2.
Really? Omega equals hertz. Omega and rad equals hertz divided by 2?
I might get my formula mixed up.
See, if you all thought about units, you wouldn't be making such an error. But you all still don't think units. All I had to say to you was that you're wrong. You tell me radians equals hertz divided hertz. That's all I had to say to you because I think units. I don't know what I have to do to get you all to think units. I've been preaching units to you ever since I met y'all. But you all just think I'm being a pain in the ass about the units. But units actually help you to think through a problem. Anybody want to try? Anybody else want to try? Omega equals 2 pi f of fs. I'm sure you all remember that now. Omega equals 2 pi f over fs. This f here is the analog f. This is digital. So if we have digital, we just solve this for f. So this is omega fs, okay, over 2 pi. That's the analog f. So to plot the x-axis, we need to know what the digital frequency, the sampling frequency was. So what's the maximum value of f going to be? What's the maximum value of f going to be? This is all the early part of the semester. What's the maximum analog frequency? And when I give this to you, you all gonna say, yeah, that's right. It's not that you don't know this. You know this, but you don't know how to apply this.
I see the formula FS must be greater than 2F, but I know you asking us for the FM specifically.
So what's your answer, Mr. Johnson?
I would say FM is half of FF.
FM is what?
Would be half of the sample.
Yes. Yes. F. What you call an FM? The maximum is pi. The maximum is digital frequency is pi. I told you that. I just told you that today. Pi divided by pi. Fs over 2. So at the digital frequency pi, that will be the analog frequency Fs divided by 2. So let's arbitrarily make the sampling frequency 10,000 hertz. The sampling frequency is 10,000 hertz. So let me go back. So this frequency here then, if the sampling frequency is 10,000 hertz, okay, what's this frequency right here? Where you have the arrow, what's that analog frequency?
.3151.
Apples. I just been bitching at you about units, and you ain't giving me any units.
Right.
Did I not say what's that analog frequency?
Hertz.
How many hertz? Let me repeat my question. This digital frequency here is pi, 3.14 rads. The sampling frequency is 10,000 hertz. So what analog frequency does pi rads correspond to?
Five gigahertz.
Yes. Yes. Let's just use that simple equation I just gave you all. Let me go back and show you the equation. See there? The analog frequency equals the digital frequency times the sampling frequency divided by 2 pi. 10,000 divided by 2 is 5,000. How is that difficult? So we use this equation in the program. So we go here. So right here we put F, the analog frequency, equals digital frequency times the sampling frequency. And a line above this, I'm going to say what the digital frequency is. The sampling frequency. Fs equals 10,000. So the analog frequency is the digital frequency times the sampling frequency. Okay, divided by 2, divided by pi. And then down here, instead of plotting versus omega, plot versus f. And then we save this. Then we run it. What's that? S equals 10. Give me a second.
Dr. Godray,
Hey,
for line 29, why you divide 2 by pi?
because if you're gonna do inline calculation, that's what you're gonna have to do. If you don't fs divided by 2 divided by pi, you have to do this instead. You have to do divided by 2 divided by 2 times pi. You need the bracket. You have to do that instead. But if you want to avoid doing that, you simply divide by 2 and then divide by pi. Have you not done 340 yet?
Yeah, we did that.
All right, let me show this to you. I don't know why students don't learn these things. F equals omega fs divided by 2 pi. So this means omega fs divided by 2 divided by pi, doesn't it?
Yeah.
Well, that's all I did. Except I wrote it in line. Omega fs divided by 2 divided by pi. Because remember, when you compute, you go from left to right. And multiplication is the same order as division. If you don't do that, you have to do this instead. You have to do omega fs divided by, what you divide by? You divide by 2 pi. This is short way of writing this. I've found that most students, when they write in line like this, get it wrong. And that's because they're not thinking about what they're doing. This step here, you go from here to here, you're saying the first thing you're doing is dividing by pi. Well, that's the top. And then what you're doing with that? What are you doing with that? You're dividing by pi. So how you all manage with your calculators, I don't know. That's why some of y'all calculate wrong. Anyway, that's off topic. Let's get back to what happened to my, what did that say? What error did that give me? FS, oh, it probably doesn't like the comma. Yeah, you see that comma there? It probably doesn't like that. Let's see if that's the case. Yeah, that was it. Oh. See there? 0, 1,000, 2,000, 3,000, 4,000, 5,000 hertz. So the point I'm making is this: because it's a digital filter, does not mean you can't plot the y-axis in dB and the x-axis in analog frequency. But to plot the y-axis in frequency f hertz, you need to know the sampling frequency. Is this clear? So the only thing we've done so far is, if you have a low-pass filter, FIR low-pass filter, you can easily convert that to high-pass filter, the equivalent high-pass filter, and vice versa. If you have a high-pass filter, FIR, you convert that to low-pass filter by doing the same transformation. Okay. That's the first thing we did. The second thing we did is the y-axis could be in dB, and the third thing we did was the x-axis to be an analog frequency F. Okay. Next thing I want to go to is sign response. Sign response. We know impulse response. What do you need for impulse response? Tell me what impulse response is.
That's the output.
Z
Mr.
inverse
Mr.
of transfer function.
Mr. Pintod. Mr. Pintod. Let me deal with Mr. Pintod first. That's the output, Mr. Pintod, is a vague statement. The impulse response is the output when what is true?
When the impulse is when the input is the impulse.
Exactly. But you didn't say that.
All right, okay.
The impulse response is the output. That's a true statement, but it's not sufficient. The impulse response is the output you get when the input's an impulse. So let me write that down. I don't know why this is not like second nature by now. We did this in 320. We did this earlier in the semester. We actually found the impulse response. The impulse response is the output. For a special case, impulse response is the output only when the input signal is an impulse. What's a step response? What's a step response?
Is only the output when input is a step.
You cracked up, Mr. Johnson. Please try again. Mr. Johnson?
Yes, sir.
Wasn't that you just now?
That was me. Yes, sir.
Please restate what you said. I just didn't hear you properly.
The step response is the output only when the input a step the step function.
Yes. The step response is the output only when the input signal is a step function. See how easy that is? I first taught you that in 320. What's the sign response? What's the sinusoidal response? What's the sinusoidal response? What's the sinusoidal response?
That would be the output when the input, only when the input sine wave.
Only when the input signal is a sine wave.
Yes, sir.
Why are you not saying that? You did it last time when there was a step. You said only when the input's a step. No, only when the input signal is a step function.
No, I think he said it just break up a little bit.
I listened very carefully what he said. And he did it again in the sine response. The sinusoidal response is the output signal. Only when the input signal is a sine wave. I certainly hope you all got this by now. Let me tell you, you better have it in 4 weeks.
What day the midterm? I mean the final one that I got it right.
24th,
All right, thanks.
last day of class. No, sorry. 22nd. 22nd is a Wednesday. Let me just check that.
Yeah, the
Hey, that's
24th
November?
Friday.
Yes, November 22nd. So you see, well, that's what, 4 weeks away? Now, cash your minds back all the way to 120, or the 320, or the 235. Tell me, how did we get the sine response, the sinusoidal response? If you're not using your mic, please turn it off. When the input was a sine wave, what did we do to get the output signal? All right, maybe let me put it in the language you probably remember most. How to find the voltage cross capacitor? Because V, V, V out of T is in fact the output voltage, and the input's a sine wave. So V out of T is the sine response, the sinusoidal response. How did we solve this circuit?
I remember we had to do some type of converting.
That ain't good enough, Mr. Beauchamp. You're going to be electrical engineer, technologist, not electrical engineer, electrical engineering technologist. You think we teach you this stuff just so you could forget it? Come on, certainly somebody remembered. Yes, convert to the phasor domain.
And it'd be one that the capacitor is 1 over S, right?
Capacitor is 1 over SC.
Yes.
Where S is what? What is S equal to?
S is J omega.
Yes, S is J omega. So what does this input voltage become? What does the input become? Let's see. 1 over J omega C. What's the value of omega? The output is V out phasor.
Wouldn't the input become 10 sine of 5 RT?
No, the input becomes a phasor. This becomes VI phasor. What's VI phase equal to? We don't know how to define a phasor? Really? 120, 235, 320, 410. And we don't know how to define a phasor? VI phase equals 10, 0 degrees. Well, you better review this because you're going to need to know that for what we're doing right now. You need to know how to find phases for what we're doing right now. What's 1 over j omega c? 1 over j omega c is 1 over j. What's the value of omega? What's the value of omega?
2 pi f.
Say again?
2 pi f.
How does that help? What's f? I can't release you all on the world. I can't let you all graduate.
That's tall, you know. Yeah.
That's what?
I was thinking tall is 1 over tall or 1 over c times r. Something like that.
Put 1,000 on top. So this is negative j, 1,000 divided by 5. It's 200, I think. Negative j 200. Okay. Therefore, V alt phase is how much? Look at this diagram. What's V alt phase equal to? Oh. We can't analyze a simple series circuit. Is that what I'm hearing?
Would that be negative 200 over?
Mr. Johnson, are you speaking directly into your microphone?
My microphone kind of I was trying to use my computer, but that was freaking out. I had to come prepared, Dark Matter. That's a technical issue.
You can't come prepared. You're not prepared because I can't understand a word you're saying. How is that prepared if I can't understand what you're saying? Either send me an answer in chat or somebody else, please. How do you find V out? How do we find V out of phase? V out phase?
I know normally it's the transfer function multiplied by the input signal.
All right, what's the transfer function? Yeah, V out phase equals H, the transfer function, times VI phase. That's a correct statement. More correctly, this is not transfer function in this instance. This is Sprig's response. Okay. I'll deal with that in a second. But right now, let's call it transfer function. Because this will be, I'm bothered with this. I am bothered with this because this is exactly what we do in digital. Except that we don't call this transfer function. We call that frequency response. How do we find the transfer function for the circuit? Or do you remember the transfer function for the circuit? What kind of circuit is this?
Will that be let me see now, that's negative J times 200.
What really concerns me is you all can't analyze a simple series circuit. After having all that training in 120, 235, 320, and 410. Let me see here. Yes, Mr. Johnson, that's right. This is simple voltage divider circuit. A simple voltage divider circuit. VL phases cross the capacitor, so it's an impedance of the capacitor divided by the sum times the supply. How many times do we do that? VL phasor equals negative J200 over 1,000 minus J200 times VI 10, 0. So in fact, this must be H. That must be H. And that's the other approach we could have taken. That's the other approach we could have taken. We could recognize this. We could recognize this as a low-pass filter. That's a first-order low-pass filter. I don't know how many times we did that. First-order low-pass filter. With transfer function, then the transfer function is 1 over S tar plus 1. That ring any bell? And so the output would be the sine response. The output would be the sine response because the input's the sine wave. Now what's torque? What's the value of torque?
That's the resistor times the capacitor.
Which is how much in this case? Which is how much in this case?
That's 1.
1 second, not 1 second. So H equals 1 over S plus 1. And now what's S? What's S? What's S?
That's J omega.
And in this case?
That's 5. J5.
No, J5 plus 1. Yeah, so that's the frequency response. This is the frequency response. And that better be equal to that. Well, let's see if it is. Right? So this here is negative J over 5 minus negative J. And is this the same as that? Well, let's multiply this top and bottom by j. So negative j squared, 1, over j5 minus j squared, 1. And j squared is negative 1, so negative times negative is 1 over j5 minus times minus is positive 1. Yes, lo and behold, we get the same answer for h. Okay? This approach is just solving the circuit. This approach is using transfer functions, realizing that this here is a low pass filter, a first order low pass filter, and the transfer function is 1 over s top plus 1. Either way, we got the transfer function. Well, the frequency response really is 1 over j5 plus 1. Okay. Let me see what this chart is. All right, so let me just recap what the important thing is. V out is a frequency response. The frequency response times VI phasor. That's the key thing. In 320 and 235 and 120, this is V out equals H, the function of J omega. Okay. H of S is the transfer function. Okay. H of J omega is a frequency response. Okay. Likewise, in digital we have H of Z is the transfer function. Okay. H of omega is the frequency response. We get this from that. Just put S equals J omega. We get this from that. Just put Z equals E to J omega. If you all had just learned your previous courses properly and retain that knowledge, this course would be a breeze because there's so much similarity. Okay. The way we define impulse response and step response and sign response, they're all the same. There's just differences in terminology, but the concepts are the same. So to get the sign response, we're going to use phases. And we're going to use VL phasor equals H of omega times VI phasor. This is what we're going to use. And it's the same principle we use since 120. Same principle, just slightly different terminology. Let's do an example. Okay. A digital filter That's difference equation. Y of n minus 0.1 y of n minus 1 equals 2x of n. Find the output. Well, find the sign response. Same thing. When x of n equals 2 sine pi over 2 n plus 60 degrees. All right, help me. What am I going to do? All right, let me remind you. What's the pertinent equation? This is the pertinent equation. So from this equation, what do we need?
You need h of z, right?
We need h of omega. We need h of omega. What else do we need from the equation? The equation back. The I phasor.
Yes, sir.
VI phasor. I didn't say anything about VN. VI phasor. And it's not VN we need. Okay. There is no VN. In this problem, there is no VI either. What's the input? The input is X.
Yeah.
The input is X phasor. The input is X phasor. And the time domain is X of n. Okay, and the phasor domain is X phasor. So this equation here is better written Y phasor equals H of omega X phasor. Because Y phasor is the output phasor. X phasor is the input phasor. All right, so what's X phase equal to? What's X phase equal to?
Is that 2 phasor 60 degrees?
No, that's 260 degrees phasor.
Yeah, sorry.
This is the phasor. This is the magnitude of the phasor. This is the phase of the phasor, or the angle of the phasor. What else do we need? What else do we need?
Frequency response.
And how do we get that? How do we get that?
We would need a transfer function.
Okay, let's go down that path. How do we get that?
Y of Z over X of Z.
Do we have to convert the Z transforms and stuff like that?
Listen. We did this weeks ago. Weeks ago. How is it y'all don't know it?
Y of Z equals 2 delta plus 0.1 Z to the power of -1.
Mr. Johnson, where you got that from?
I was looking at the difference equation.
Yes, look at the difference equation. Take the Z transform of this difference equation for me. Y then becomes?
But that's only for FIR filter, right?
No. You can find the Z transform of any equation. As a matter of fact, how do you find this if you can't find the Z transform?
No, I wasn't meaning the Z transform. I just mean we were trying to find H of N.
I didn't say anything about H of N. Mr. Johnson, what's the Z transform of this difference equation?
What I did was the negative 0.1, right? One. I
Y of N. Okay. I can't take any more nonsense. Let me just tell you. Y of N becomes Y of Z. Okay? Minus 0.1. 0.1. Y of N minus 1 is Z to the -1 times Y of Z. Okay? 2 times X of Z. Select like terms. Y of minus 0.1, Z to the -1, Y of Z equals 2X of N. So Y of Z over X of Z is 2 over 1 minus 0.1 Z to the -1. There it is. There's your transfer function. And again, why y'all don't know that, I don't know. So there's your transfer function. 2 divided by 1 minus 0.1 Z to the -1. But it's not H of Z we want. It's H of omega we want. So what do we do? How do we get H of omega?
Wherever we see Z, we put e to the minus j.
No, where we see, we put e to the j
E to the j.
omega.
Yeah.
2 over 1 minus 0.1. And because of -1, it becomes e to the minus j omega. Okay. Now, what's the value of omega? What's the value of omega?
And we saying highest value of omega is pi, right?
I am asking what is the value of this omega in this problem?
The value of this omega is omega over 2.
No. Pi over 2.
Yeah, pi over 2, sorry. Yeah, because you read the number in front of n.
That's omega. So h of pi over 2 is 2 over 1 minus 0.1 e to the minus j pi over 2. Right? Or another way of writing the same thing is 2 e to j pi over 2 over e to j pi over 2 minus 0.1. We could do that. We don't have to do that, but we could do that. And then the top, e to j pi over 2 is simply j. Anyway, we won't go that way. This here is simply 2 cosine pi over 2 plus j2 sine pi over 2 over the bottom. And the bottom is what? Cosine pi over 2 minus 0.1 plus j sine pi over 2. Go to the next page. Okay. So h of pi over 2 is 2 cosine pi over 2, that's 0. That's just j2 on the top. The sine pi over 2 is 1 over the bottom. So that's 0 minus 0.1 plus j1. So in this case, it's real easy. This case is just j2 over negative 0.1 plus j1. That's 2 90 degrees. What's the bottom? What's the magnitude of the bottom? What's the magnitude of the bottom? Mr. Johnson, you're a talking fool.
Oh, my mic was off. I was talking. You didn't hear me?
No, I can't hear you if your mic is off.
I'm sorry. It's 1.005.
Yes. And what's the angle?
The angle is... I got negative 84.29.
I saw you did. Look again. What quadrant? What quadrant is that number? I don't know why I have to do this every time. What quadrant is that now? Huh?
That in the fourth quadrant.
Don't talk fool.
Hold on. You see? No. That in the second quadrant.
So what answer are we expecting?
That should be a number greater than 90. So it's
Anyway, I'm running out of time here. It's 95.7. 95.71. And if you don't know how to get that, I suggest you relearn it. I've taught it to you many times. And you just don't remember it. Or you never bothered learning it in the first place. So this is 1.990, and the angle is 90 minus 95.71 minus 5.71. Okay. So that's H. So Y phasor equals H of pi over 2 times X phasor. So Y phase is 1.990, negative 5.71 times X phasor, and X phasor is what? 2, 60 degrees. So the output is 1.990 times 2, 3.98. 60 minus 5.71. 54.29. So Y of n then, Y of n, back to the time domain, Y of n equals 3.98 sine of pi over 2n plus 54.29 degrees. And again, this problem should be really easy for you all because of all the work we did previously on phases. Any questions about this? So this is the sine response then. This is the sine, Y of n is the sine response due to the input, due to that input 2 sine pi over 2n plus 60 degrees. Any questions or concerns? If you still can't find the magnitude and phase of a complex number, I don't know when you're going to learn it. I've been teaching this since 120, and you got it in 168. Okay, since I hear no questions or comments, we can call it a day. So I'll see you on Wednesday, Lord willing. I'm giving you a lot of information every class. If you don't study that information, you will not learn it. If you do not learn it, you will not pass. It's as simple as that.